Shown in the figure below is a circuit containing 3 resistors and 2 batteries. All resistor values are labeled in ohms. We recognize this as a Kirchoff problem, and the only thing that's really unusual about the Kirchoff problem is the fact that the circuit itself has been drawn in a distorted manner in an attempt to confuse us. It's not going to confuse us. We're going to begin, like we do most Kirchoff problems, by identifying the junctions. There are 2 of them, as shown by these green dots. And then we're going to draw arrows that go from one junction to the other and label arbitrarily our current names and their directions. The first current I'm going to place over here, and we'll call this one I1. The second current I'm going to run this way, and we're going to call that one I2. And finally, for the third current, I'm going to run it this way, and we'll call that one I3. If you're concerned at this point that at least one of these currents seems to be pointed in the wrong direction, different than you would imagine, you're right. No one cares when you draw a Kirchoff circuit which way you draw the arrows. You draw them in any direction and then you wait for the answers to be negative. In that case, the mathematics tells you that you had the wrong sign convention. And in fact, I think most likely I3 is in the wrong direction, and possibly even some other currents, but I don't care. To solve the Kirchoff problem, we always proceed in the same manner. We walk as many loops as is necessary to cover each and every circuit element at least once, and then we finish with a junction equation. I'm going to start a loop at the red dot that I have drawn in this lower corner, and I'm going to walk the loop through the 4 ohm, 5 ohm, and 10 volt battery in that order, meaning that I'll be walking clockwise. As I encounter the 4 ohm resistor, I recognize that there will be a voltage difference, V equals IR, so there will be a 4 ohm times I1 delta V, and I realize that since I am walking with the current, and current flows downhill, this will be a negative 4 times I1. The second item I encounter while walking this loop is the 5 ohm resistor, and in that case, since I am walking in the same direction as I have labeled I3, I am going downhill, and therefore downhill is a negative, and I have I times R, or R, 5 ohms, times I, which is I3. Finally, we're going to cross the 10 volt battery. When you cross a battery, the sign that you get does not depend upon the direction of the current. Instead, it depends upon the orientation of the battery. In this case, we're going from the positive to the negative of the battery. Therefore, we are again going downhill, and we will have minus 10 volts. Kirchoff's loop law is that the change in voltage around any closed loop adds up to a total of 0, and so this completes our first loop equation. If we're to write a second equation, we need to find at least one circuit element that has never before been used in a loop equation and use that. We actually have 2 elements that have never been used in loop equations. These are the 5 volt battery and the 2 ohm resistor. So what we're going to do is we're going to walk a loop that includes those, and we're going to start at this second red dot, which is actually located at one of the junctions. We're then going to walk through the 10 volt battery, the 5 ohm resistor, the 2 ohm resistor, and then through the 5 volt battery in order to return home. First we go through the 10 volt battery, and since we're climbing from the minus to the plus side of that battery, that will be a plus 10 volt change. As we cross the 5 ohm resistor, we are going against the current. Against the current is uphill. So that's going to be plus 5 I3. As we cross the 2 ohm resistor, we are also going against the current I2, therefore it is uphill for 2 ohms times I2. And finally, when we cross the 5 volt battery, we are going from its plus to its minus. That is 5 volts downhill, and we have completed our cycle, and the sum of all voltage changes around a closed circuit must be 0. At this point in the analysis, we recognize something very important. We have used every one of our circuit elements in at least one loop equation. Therefore, we cannot draw another loop equation because that one would not be independent of the previous 2 equations that we had. In order to get a third independent equation, we're going to have to resort to imposing Kirchoff's junction rule. And in this case, we take any one junction. I'm going to take the top junction, And as far as the top junction is concerned, we take the sum of all currents going into that junction. I see that I1 is going into it based upon the green arrow. I2 is also going into this junction based upon its green arrow. However, I3 is leaving, and the junction rule is the sum of all current entering equals the sum of all current leaving. Once again, we're going to solve this problem by invoking Cramer's rule, and to do that we begin by writing all three equations in the neatest possible form. I'm going to begin with the junction law by moving all of the unknowns to the left-hand side of the equal sign, in which case we have I1 plus I2 minus I3 is 0. Translating the middle equation, we notice that it has an I2 term and an I3 term. We're going to leave those to the left-hand side of the equal sign so that we have twice I2 plus 5 times I3. And we'll move all the constants to the right-hand side of the equal sign, producing a total of negative 5. Finally, the last equation, we'll leave the unknowns on the left-hand side of the equal sign. So we'll have a minus 4I1, no I2 term, a minus 5I3, and positive 10 on the other side of the equal sign when we move the negative 10 across. Cramer's rule tells us that we are simply able to write down the answer for every one of our three unknowns as the ratio of two determinants. The bottom determinant simply contains the coefficients found on the left-hand side of the equal sign. This bottom determinant is the same regardless of whether we were calculating I1, I2, or I3. The numerator determinant, however, depends upon what you're calculating, because what we will do is we will take the three quantities to the right-hand side of the equal sign and we will substitute those into the determinant in the column for the one unknown we're trying to solve for. Since at this point we're trying to solve for I1, we will put these three numbers, 0, minus 5, and 10, into the I1 column. After that, the I2 and I3 columns are just the same as they were in the denominator determinant, and we're now prepared to solve for both the numerator and denominator. We're going to do this by the method of drawing a ghost determinant, which is a copy of a determinant to its right, and we're going to begin in the denominator. The three positive diagonals begin in the top row and go to the right of the real determinant, and we multiply along diagonals. The product of 1, 2, and minus 5 is negative 10. The product of 1, 5, and minus 4 is negative 20. And the third positive diagonal has two zeros, so the product is 0 and makes no contribution. We then move on to the three negative diagonals, where we will subtract the product of three numbers. In the first such negative diagonal, we have a 0, so it drops out. And also for the second negative diagonal, we have a 0, and it will drop out as well. For the third negative diagonal, minus 1 times 2 times minus 4 is positive 8, and we must subtract the positive 8. This completes the denominator, and for the numerator, we do the same convention by writing the ghost determinant. After this, we're ready to begin calculating our diagonals. The first positive diagonal contains a 0 and drops out. The second positive diagonal has 5 times 10 for a positive 50. The third positive diagonal has a 0 and drops out. The first negative diagonal has a 0 and drops out. However, the second negative diagonal has a product which is a total of positive 25. Therefore, since it is a negative diagonal, we must subtract positive 25. And then finally, for the last negative diagonal, the product is the number negative 20, and when we subtract negative 20, that's the same as adding 20. And thus our final result for I1 is negative 45 over 38, keeping true what we anticipated, and that is that at least one of these three answers is in fact a negative number. We follow exactly the same procedure to calculate the currents I2 and I3. Cramer's rule tells us that each one of these two quantities is the ratio of two determinants, and for the denominator determinant we already know the answer. The denominator is negative 38 based upon our previous calculation. However, the numerator will be unique because we need to replace the I2 column with the three numbers from the right-hand side of the equal sign. That's the 0, the minus 5, and the 10. The I1 and I3 columns are as they would be in the denominator determinant, and then we become ready to solve for the value of the numerator determinant by using the technique of writing a ghost determinant. To solve for the numerical value of this 3 by 3 determinant, we will calculate the 3 positive diagonals, subtract from them the 3 negative diagonals, and be all set. The first positive diagonal gives us a total of 25. The second positive diagonal gives us a 0, and so does the third positive diagonal. Moving on to the negative diagonals, we see that the first negative diagonal gives us a product of 50, and we must, of course, subtract this 50. The second negative diagonal gives us a 0, and the third negative diagonal gives us negative 20. Subtracting negative 20 is the same thing as adding 20, meaning that we then get the result for current I2 being positive 5 over 38, meaning that the I2 arrow in our figure was actually drawn in the correct direction. Finally, we calculate I3 again by using Cramer's rule. The denominator will be the same as the calculation for I1 and I2, and what makes this calculation unique from those two is the fact that the numerator determinant is different, and it is different because the 3 numbers from the right-hand side of the equal sign in our neatly ordered equation are plugged into the I3 column rather than the I1 or I2 column. The I1 and I2 columns take the values the same as they would take in the denominator's determinant, and once again we can solve for this determinant by drawing its ghost. The first positive diagonal gives us a plus 20. The second positive diagonal also gives us a plus 20. The third positive diagonal has a 0 and cancels. The first negative diagonal has a 0 and cancels. The second negative diagonal has a 0 and cancels, and the third negative diagonal has a 0 and cancels, meaning that we have now calculated the entire result for the current I3, and the current I3 is equal to negative 40 over 38. As predicted, at least one, and in fact 2 of these currents turned out to be negative, and we don't care. That's perfectly fine. That gives you 100% credit on an exam. What we would like to do is make sure that these answers are right. Now, if we were to plug them into the junction equation, it's quite easy to see that negative 45 over 38 plus 5 over 38 is indeed negative 40 over 38. However, the junction equation does not exercise testing the denominator calculation from our Cramer's rule. For that reason, we're going to select a different equation from the set, and we're just going to arbitrarily choose the one that tells us that twice I2 plus 5I3 should be equal to negative 5, and this is what we'll test by plugging in on the left-hand side of the equal sign. Twice 5 over 38 is 10 over 38, and 5 times 40 is 200. Combining these terms gives us negative 190 over 38, which indeed does equal negative 5, demonstrating that we have solved our Kirchoff problem correctly.